Hello everyone, here's another Physics 30 example set. This one is from Unit 6 on nuclear theory, and this is Lesson 5, which is fission and fusion. Of course, fission is when atomic nuclei join together and release energy, and fission is when a single atomic nuclei splits apart and releases energy. So here we have... what do we have? Oh yeah, Einsteinium-253, there it is. Einsteinium-253 bombarded with an unknown particle. So let's go ahead and start writing our statement. So here we know the annotation, it's ES, and the 253 is the isotope number, which is referring to the number of nucleons. So let's just give ourselves some reminders. Anything in red is the number of nucleons, which is protons and neutrons. And this is a conservation law. This is going to be essentially conservation of mass. Conservation of mass. And the 253 is saying that there are 253 atomic mass units in terms of masses. That's what we have. Now, it's Einsteinium, so we have to look that up on our periodic table, and we probably can do that quite quickly. If not, we remember that Einsteinium is 99. If you're a hockey fan, of course, that's Gretzky's number, so that's a good way to remember it. But this is also part of our conservation law. This 99 is the atomic number, and this is to do with the number of protons, but actually really it's the number of charges. So we call it the atomic number, and it's really just conservation of the number of protons, but essentially it's the conservation of charge. And since there are 99 protons, that means there must be 99 elementary charges. That must be, well, this conservation of charge and conservation of mass must be conserved throughout. Okay, so something is missing. We are missing this bit of information, and that's what we're going to try and find out. We're told that as a result of this bombardment, we are producing Mendelevium, so MD256. I'm liking this scenario already. We've got two very influential, famous, legendary scientists being named in our periodic table, Einstein and Mendeleev. Anyway, let's carry on. So we've got this Mendelevium, it's created, and a neutron, a single neutron. So we can't forget that, we must have that on there as well. So whatever it is that hits the Einsteinium, it's managed to dislodge or break away a neutron. Okay, so we have this neutron, which has a 1. Oops, other way around. That was a rookie error, a 1 and a 0. Why is that a rookie error? Well, I got that mixed up for a second there. I'm looking at the number of nucleons, and of course the conservation of mass. The mass number for a neutron would be 1 atomic mass unit, and very importantly, the charge of a neutron, of course, is 0. So these are the two conservation laws we want to keep track of. Let's also just highlight this 256. Okay, so we have got, on the right side of the equation, on the product side of the equation, we have 256, let's just do it here, 256 plus 1. So, of course, that's 257. So this must be conserved. So over on this side of the equation, on the product side of the equation, we have 253 plus something unknown has to also equal 257. Well, 253 plus 4, 253 plus 4 gives us that answer. And so this is probably giving it away for you right now. Oops, I've used the wrong color. I wanted to use blue. Let's go ahead and put that in. 4 is the nucleon number, the number of nucleons in this particle. Let's carry on and do the conservation of charge. Well, Mendelevium is, what is it, 101. It's 101 on its atomic number. So 101, there we go. Let's put that in green. Let's do the conservation of charge. On this side of the equation, on the reactant side, we have 101 plus 0. So that's a grand total of 101. Okay, which means on this side of the equation, we also must have to have 101. Let's make sure we do. So it's going to be 99 plus whatever it is that's missing here. And yep, you guessed it, it's 2. So we can come up and put that in here. Of course, this is looking a lot like something you should be very familiar with, which is, of course, an alpha particle. So the unknown particle, the particle that did the bombarding, is this here alpha particle. Okay, so for example, number 2, we go through the same process. This time we have uranium, which is the isotope 235, and it's bombarded by a slow-moving neutron. Slow-moving just means it doesn't have much kinetic energy, so we can essentially ignore any extra energies in this. So there's our neutron, 0 and 1. Uranium, of course, is the atomic number 92. So this is going to split into 2 smaller nuclei, one of which is zirconium. So let's put that on here, zirconium isotope 96. Zirconium on the periodic table has atomic number 40, plus, what are we told? 3 neutrons. Well, there's going to be something, the bit that we're missing, it's going to be here, that's a daughter nuclei, plus 3 lots of neutrons. Okay, so let's keep track of these top pieces. This is 235 plus 1. So 235 plus 1 means we are keeping track of 236 atomic mass units. That's our conservation of mass. So the mass has to stay the same. So over here, we're going to have 96, which is this guy here, plus some unknown number, which we don't know, plus 3 lots of 1, because we have 3 neutrons. So we can't afford to forget the 3. It's a common mistake to do that. Please don't make that mistake. I know you won't. Good. So 96 plus 3, and this missing value must equal to 36, because the masses must, these masses must be conserved. They must be the same. Conserved. Okay, so we can, what can we do? Oh, right, yeah, we're going to go 96 plus 3, well, that's 99, and then 99, well, what 236 minus 99 is going to give us 137. So this guy in here must be 137, which means this here is 137. So whatever it is, it must have 137 protons and neutrons. In other words, an atomic mass unit of 137. Okay, let's figure out what it actually is. So down here we've got 92, so we have to have 92 charges. That would be the elementary charge, plus, well, 0, because neutrons do not have an elementary charge. So it's got to have a total of 92. Okay, over this side we have 40, so we've got 40 plus, well, this is where we're going to have our space. We're not sure what that is. Plus 3 lots. Oh, let me just put my space in. So this missing bit, whatever we are missing, plus 3 lots of 0, which of course is 0. And this also must equal 92. Remember, same principle as before. This is my charge. This is my charge over here. These must be conserved. Okay, so we can do the math. We can go 40 plus 0, and then 92 minus 40. Well, that's going to give me 52. So I can put that in here. 52 is the missing number. Up here, I'm going to go 52. And now I can look at my periodic table and see what it is that we've produced as one of our daughter our daughter nucleus is? Well, it's on my periodic table. It's tellurium. Okay, so there it is. There's the missing daughter nucleus. It's tellurium, and if I was to write it down as its isotope, it would be tellurium and 137, the isotope.